Hi everyone, and welcome to the fourth and final video going through some past exam questions on the topic of the halogens. Here we've got another one of these longer questions. It's a 6-mark question here, so this is similar to a question we saw in a previous video. But they're students investigating the reactivity of the halogens and adding bromine water to solutions of sodium chloride and sodium iodide in separate test tubes. Then they added the cyclohexane and shake it. State what colour you would see in the cyclohexane in each tube. Write ionic equations for any reactions and state and explain the trend in reactivity. Okay, so if we talk about bromine water plus sodium chloride, okay, if I react bromine with sodium chloride, then the bromine is not going to be able to displace the chlorine. Okay, so let's put that. Bromine cannot displace chlorine. So there's no reaction. What colour would we see in the cyclohexane? So the bromine water would still be left over. So an orange colour would be seen. And we can't write an ionic equation because there hasn't actually been a reaction. Okay. Right, what if we react the bromine with the sodium iodide? Okay. Here in this case the bromine will displace iodine. So bromine can displace iodine. So therefore let's write the equation. We're going to get the bromine is going to react with the iodide ions, and we're going to end up with bromide ions and iodine going into the solution. Okay, and a purple colour would be seen because we've got the cyclohexane. So right, state what colour you would see. We've done that. Write ionic equations. We've done that. State and explain the trend in reactivity. Okay, so this shows that the trend in reactivity is chlorine is more reactive than bromine, more reactive than iodine. And we can say the halogens get less reactive down the group. And then it does say to explain the trend in reactivity, so we need to say why. Okay. This is because as you go down the group, the atomic radius, do you remember talking about these factors? It's the atomic radius and the shielding. Atomic radius and shielding increase. So there is a weaker attraction between the nucleus and the outer shell. Therefore, elements further down the group find it harder to gain an electron. So it's quite a nice question. We've got a bit of the explanation, we've got a bit of ionic equations, we've got a bit of colour changes, we've got a bit of displacement reactions. It's quite a nice kind of summary of a lot of the things that you need to know about the halogens in one question there. And then here, suggest why the student carried out the reactions in a well-ventilated area. So this is because we don't want to be breathing the stuff in because it's going to be toxic, but we need to be careful here because what I think the most common thing is we've got, I remember chlorine is toxic. But if we look at the reactions that we've done, we're not actually making any chlorine. Yeah, in this reaction we've made iodine, and there was no reaction there. We didn't actually make any chlorine, so it's not chlorine that's going to be toxic. Iodine is not particularly toxic. Bromine is going to be the problem, right? We don't want to be breathing bromine in. Okay, so that's what we're going to say. We can say that the bromine is toxic. They will not give you a mark if you said chlorine is toxic because you're not making any chlorine, so you do need to be careful with that one. Right, we've got a few extra questions here to look at. Most of these, again, are similar to ones that we've seen before. So here it's saying bleach can be made by reacting chlorine with cold aqueous sodium hydroxide. It's nice, they're giving us one of the products, they're giving us a bit of a clue. We need to write this equation. This is one of the equations that we need to know, isn't it? So it's chlorine and sodium hydroxide. It makes our NaClO, which they've given us, that was nice of them. And it makes NaCl, and it makes H2O. Okay, this is the disproportionation reaction that we've seen before, where chlorine goes from 0 to +1 and 0 to -1. Okay, and then in terms of balancing it, we need 2 there, so that we've got 2 sodiums and 2 oxygens and 2 hydrogens and 2 chlorines. Right, the systematic name for NaClO is sodium chlorate 1. Remember, the 1 is telling you that the chlorine is oxidation state +1. We also end up with this NaClO3, which, if you remember, comes from the reaction of chlorine with hot concentrated sodium hydroxide. So what's the name of this? Well, it's sodium chlorate again. We just need to put a different number to represent the oxidation number of chlorine. So what are we going to have? Sodium's oxidation number is going to be +1. Oxygen is -2, but there are 3 of them. -2, -2, -2. So that's -6. +1 is -5. So the chlorine must be in oxidation state +5 to get it to balance out. So this is going to be sodium chlorate 5. When it's heated, this isn't a reaction we've seen before, so it's a different one, but it's a disproportionation. Using oxidation numbers, explain why it's disproportionation. So we've done this question, just not with this reaction. So using oxidation numbers, so let's have a look. It's going to be the chlorine that's going to change oxidation number here. So we've already seen that this is oxidation state +5 because we worked it out from here. What's going on here? This is +1. Oxygen's -2, and there's 4 of them. So we've got -2, -2, -2, -2. So we've got -8 +1 is -7. So here the chlorine must be +7. And here we've got +1 and -1. Okay. So we can say chlorine is oxidized from +5 to +7 in the NaClO4. And we can say that chlorine is reduced from +5 to -1 in NaCl. Chlorine has been both oxidized and reduced. Therefore, this is a disproportionation reaction. Remember, that's what disproportionation means. It's when you've got the same element being both oxidized and reduced in the equation. Right, the final question here says, chlorine has been added to drinking water for over a century. Recently, some scientists have put forward the case for not chlorinating drinking water. This is because chlorine may react with organic compounds, so to form chloromethane here. So state one valid reason that supports the scientist's case and one reason why chlorine should be added to drinking water. Okay, so we've seen this before. We need to worry about these chlorine compounds because chlorine compounds may be carcinogenic. So that's one reason not to do it. One reason that chlorine should be added to drinking water is, well, what was the point of doing it in the first place? Just chucking chlorine in the water for no reason, right? There must be a reason for doing it. One reason that chlorine should be added to drinking water is because it kills bacteria. And then we, as a society, need to decide the risks and the benefits, right? And I think overall, the risks of the bacteria that would be in the water if the chlorine wasn't there are much greater than the risks caused by these chlorine compounds.